In this tutorial, we will demonstrate how to verify the characteristic impedance of a coaxial transmission line. First of all, let's take a look at the physical construction of a coaxial transmission line, which is shown in the figure here. We have a center conductor which is separated by a dielectric material from the outer conductor, and then the outer conductor is protected by a plastic jacket. Now, if we have a look at the cross-section of a coaxial transmission line, we can define three main parameters for this type of line. The diameter of the inner conductor, which we'll call di, the inner diameter of the outer conductor, which we will call do, and then the dielectric constant of the dielectric, which is interposed between inner and outer conductor, which we'll call Er, and is usually referred to as epsilon r in the literature. So let's get started, and as usual we'll click on Circuit Schematics, select a new schematic, and because we will be verifying the impedance of a commercially available cable called RG58, we'll call the schematic RG58. The RG58 cable is very commonly used at RF and is widely available. So the first element that we need to fetch is a coaxial transmission line. This is available in Microwave Office. We can just press Ctrl L and then search for an element called coax. Notice that we are searching by name since the funnel is on the name heading at the moment. And then we can find this coax element right here, double click on it, and then place it on the schematic like so. Let's take a look at this in a bit more detail. Di is the diameter of the inner conductor, Do is the inner diameter of the outer conductor. The length we will be looking at a little bit later on. This is just the physical length of the line. Er is the dielectric constant epsilon r, or the dielectric between the inner and outer conductor. And then we have two extra parameters which allow us to account for losses. The T&D element accounts for losses in the dielectric material, and ρ accounts for the finite conductivity of the metal that we are using. However, in this tutorial we won't be bothering with the losses. We'll just keep those two last parameters to what they are. Now, what do we do with these terminals? If we have an unbalanced system, which often we do, we of course need a ground reference. And it is customary to connect the outer conductor of the coaxial line to ground. So what we need to do is get ourselves a couple of ground connections, we press Ctrl G, to be able to ground the outer conductor of our coaxial line. This way now, terminals 1 and 2 are the input and output of our transmission line respectively. Now let's set some of these parameters to the values that are given in the datasheet of an RG58 cable. The inner diameter of this cable is 0.81 millimeters. The outer diameter, or rather the inner diameter of the outer conductor, is 2.9 millimeters, and the dielectric constant of the dielectric which is used for this cable is 2.3. Now that we've done this, we need to verify the impedance of the line. We expect it to be 50 ohms. How do we do this? Again, here we have to refer to the manual and the technique that is explained there for verifying the impedance of our transmission line. What we need to do is set the length of the transmission line to 1/8 of a wavelength, and then if we terminate our transmission line with either an open or a short circuit, and then measure the modulus of the impedance as seen at port 1, this will give us directly the characteristic impedance of the transmission line. So let's go through this process step by step. If we want our transmission line to be 1/8 of a wavelength long, we first have to calculate the wavelength. Now, the wavelength is proportional to the velocity of propagation. In this case, because we have a dielectric between our two conductors, the velocity of propagation will be somewhat lower than the speed of light. It will be lower than the speed of light by the velocity factor, which is calculated as 1 over square root of epsilon r. So the velocity of propagation of the signal will be 1 over square root of epsilon r times the speed of light. So now that we've calculated the velocity of propagation, which turns out to be approximately 1.97 times 10 to the 8 meter per second, in order to calculate the wavelength, we need another parameter, the frequency. In a simulation, we can pick any frequency that we want, within reason. But to make the calculations as easy as possible, we will just pick a very straightforward one. We'll choose the frequency to be 1 GHz. So the wavelength, which is the velocity of propagation over the frequency of operation, turns out to be roughly 197 millimeters. But of course, what we want is 1/8 of a wavelength, so we have to divide the wavelength by 8. And this gives us a value of 24.6 millimeters. So now we can go back to our schematic, and first of all, we can set the length of our line to 1/8 of a wavelength, which is 24.6 millimeters at 1 GHz. Remember, this length is frequency dependent. Then we can terminate our line with either a short or an open circuit. You can use either or. I would normally use a short circuit in simulation, but in a laboratory environment, an open circuit is probably easier to realize. So let's get ourselves another little ground connection to short circuit our line. And then what we need to do is insert a measurement port, which allows us to see the modulus of the impedance as seen by port 1, i.e. the input of our transmission line. And the modulus of this impedance will give us the characteristic impedance of the line. Of course, we have to make sure that we are simulating at the right frequency, the one for which we've carried out the calculation of the length. So we can go to Project Options, double click, and then we need to select single point, put 1 in there, click on Apply, and then OK. So we're all set up to go now. All we need to do is to go to Graphs, right-click on Graphs, select a new graph, and it'll be a rectangular graph. We'll call it RG58Z0. And then we need to add the measurement to see our characteristic impedance. We right-click on the graph, go on to add a new measurement, then select Z as the measurement, because we want the impedance, seen at port 1. And in terms of the data source name, it will be, of course, the schematic RG58. Now, remember that we're looking for the magnitude of the impedance, so make sure the magnitude here is selected. Click on Apply, and then OK. Now, simulate. You can see that we are very, very close to 50 ohm here. So this goes to show how powerful and accurate the simulator can really be. And it also demonstrates the validity of the technique that we explained in the manual for the verification of the characteristic impedance of our transmission line. Now, what would be interesting to look at is how the characteristic impedance of a line varies as the diameter of the inner conductor is changed, and also as the inner diameter of the outer conductor is changed. So we can work out the dependency of Z0 on the inner and outer diameters of our coaxial line. So what we're going to do is duplicate the schematic that we currently have. Of course, we can do this in one or two ways. We can right-click and then select Duplicate Schematic, or more simply, we can simply drag the schematic onto the circuit schematic heading, and this will create a new schematic. And we can then rename the schematic. We can call this Z0 versus DI and DO. So what we want to be able to do here is to see the impedance of the transmission line versus various values of the inner diameter and versus various values of the outer diameter. So let's start with the inner diameter. How can we assign a range of value to this parameter? We can simply use a swept variable. So what we do is first of all get ourselves an equation by clicking on the icon in the toolbar up here. And this will allow us to specify a variable name to which we can then assign a range of values. We'll call this variable inner diameter, and we also have to assign an initial value to it. We'll just say 1. This is completely immaterial. We just need to assign an initial value to this variable. Is one of the rules of the simulator. So at the moment we've just declared a variable which has got a single initial value. What we want to do is assign a range of values to it, and we do this with a swept variable element. We can find that yet again by pressing Ctrl L and then typing SWP, and you can see that we get a swept variable control element right here, which is just what we're looking for. So let's double click on that and then place it on the schematic like so. We can click on the View All icon to give ourselves a bit more space. Then the variable name here will have to be the name of the variable that we just declared and initialized. So we can double click on there and type inner underscore diameter. Then we need to select a range of values. We can double click on this element, and you can see that the values could be defined here in between curly brackets as a list. For example, you could type 0, 0.5, 1, and this would give you 3 values in your values range. However, this can be cumbersome if we want to create a wider range. And there is another simpler way to create a range by just giving an initial value, a final value, and an increment. So I can just remove this bit and type in stepped, and then I need to put the initial value first, let's say 0.8, then the final value separated by a comma, let's say 2, and then we can insert the step, which we'll pick to be 0.01. So now we've assigned a range of values to our swept variable, which is between 0.8 and 2 in increments on 0.01. Click on OK. Now the last thing that remains to be done is to change the value of di for our coaxial line to the swept variable that we've just declared. So we type in here inner diam, and this means now that the value of the diameter of the inner conductor will be swept across the range that we've declared in the swept variable control element. This will allow us to now display the characteristic impedance of the line versus the diameter of the inner conductor. To do this, let's go to Graphs, open a new graph. It'll be a rectangular graph yet again, and we can call this Z0 versus di. And then we just right click on the graph, go on to add a new measurement. Again, we want the Z measurement, the impedance measurement at port 1, but this time, make no mistakes, we have to use the new schematic, the one that has got the swept variable control. Now, in terms of the sweep frequency, we've only got one frequency, and we don't want to use it for the x-axis. We just want to either plot all traces, which is just one trace, or equivalently, we could have selected frequency equals 1000 megahertz. In the case of one frequency, these two choices are identical. And then the swept variable we want to use for the x-axis. So we need to select use for x-axis. And this way we'll get the plot of the characteristic impedance versus the diameter of the inner conductor at 1 gigahertz. Click on apply and then OK. Then simulate. Now you can see how we're starting from a diameter which is very similar to the one we had before, so we're starting around 50 ohms, and then as the diameter of the inner conductor increases, the characteristic impedance of the line decreases. This is very simply explained, because if you think about it, we are making the cross-sectional area of the inner conductor much larger. This allows for much more current flow, and because the impedance is voltage divided by current, if the current increases, then the impedance decreases. Now that we've seen how the characteristic impedance varies with the diameter of the inner conductor, we want to see how the characteristic impedance varies with the diameter of the outer conductor. So, first of all, let's rename our schematic here to Z0 versus di, to avoid confusion, and then we can duplicate the schematic by dragging it into the circuit schematic heading, and then we'll then rename it and call it V0 versus DO. So now what we need to do is just manipulate our swept variable so as to be able to sweep the outer diameter rather than the inner diameter. So first of all, we'll set the inner diameter back to what it was, we'll say 0.81 millimeters. Then we'll change the name of this variable to outer diameter, just to make sure we don't get confused. And of course we need to carry out this change throughout. And then the values that we use, of course, will also be different. We will select a different range here, starting from 2.9 and then ending at 8 in steps of 0.05. So now the last thing that's left to do is to assign the outer diameter variable to DO. Now we can go to Graphs, open a new graph. It'll be a rectangular graph. We'll call it Z0 versus DO. And then again we right click to add a new measurement, and it'll be the impedance measurement coming from the Z0 versus DO schematic. we want the impedance at port 1. As frequency, we will just say plot all traces. And then for the swept variable, we'll make sure that it is used for the x-axis. Click on apply and then OK. Then simulate. Now you can see that what happens in this case is the exact opposite. So as we increase the inner diameter of the outer conductor, we end up increasing the impedance. So there is a direct proportionality. We are starting from around 50 ohms, of course, because this is the value for the RG58 cable. But as then we make the diameter of our outer conductor larger and larger, our impedance also increases. And this is easily explained because if you think about it, when you make the diameter of the outer conductor larger, this means that the distance between the outer and the inner conductor is larger as well. And because the voltage is proportional to the distance between the two conductors, then when we have the conductors further apart, we have a higher voltage. And because we have a higher voltage and the impedance is voltage divided by current, then of course the impedance increases.